There we go. All right, now we're live. Woo. Oops. Okay, there we go. Haha. Sorry. Checking settings. Everything is good. Hey, Connor. Welcome. Aren't you? I think like kind of odd time to be streaming chemistry stuff because it's whatchamacallit, spring break, but that's okay. Anyways, I hope I actually have the right term 1 review because I've neglected to actually bring a copy with me. You let me know if this is the wrong one. Although admittedly, if it's not the one I gave you guys before the break, not a big deal because it kind of covers the same information. And we'll just go over it. It shouldn't take too long, I don't think. Don't forget to do the Kahoot challenges as well. They should still be available for another week or so. And I think the answers, it'll tell you if you got it right or wrong. If there's anything I messed up, because it's quite possible I misclicked the answer, fire me an email or let me know when you guys get back from spring break. Okay. No, I think I'm an hour early, Connor, from when chem class is normally at. Because we have chem last block of the day on Mondays. Yeah. I tried, but I have to pick up Penny gets off of school at 2:30 and her school is off of spring break right now. They're back in school today, so yeah. Anyways, so let's get started then with my term 1 review. So as a quick reminder, I don't have my pen. There's my pen. So quick reminder, term 1 will cover basically, what did it cover again? Reaction kinetics. That's the first unit, reaction kinetics. Then equilibrium was the second unit. And then the third unit was solubility, equilibrium. Okay, and I think I mentioned that like this equilibrium is it's going to basically be the rest of this semester, because after spring break we'll start talking about acid-base equilibriums, and then after that we'll talk about electrochemistry, which is basically more equilibrium. Anyways, so going through this review, reaction kinetics, we discussed which reactants generally react, or sorry, how things react. And for reactants that act slowest, generally the solids will react slowest, and that's because they don't move. They don't have translational motion, or very, very little translational motion. If you remember my Chem 11 demonstration of what translational motion was, then yeah. Gases and liquids tend to react faster. These are faster reacting because of translational motion. But they are not the fastest. The fastest ends up being aqueous. These are the fastest in general. Part of the reason they're the fastest is because they have both translational motion plus near infinite surface areas because of the way that aqueous reagents are arranged. So fastest because of large surface area, and they have lots of translational movement. Okay, between liquids and gases will react faster than liquids because they have also increasing surface area and they've got increased translational motion. So the basic idea is that if you want reactants to react fastest, you want to give them as much translational motion as possible, and you want to give them as much surface area as possible. Okay, that combination will make them react super fast. Okay, the second question, we discussed how to measure reaction rates in this unit. So basically anything that you can measure with a number. Okay, so anything that can be measured with a number is a good method of measuring a reaction rate. And basically the only thing that you can't, anything that can be given a number. And the only thing that you really can't give a number is like smell, because we don't have any kind of numerical scale for smell. One of these days we might, but currently we don't. So measuring a smell is not a good way of measuring a rate of reaction. But again, if we have a numerical method of measuring a smell, then that would also be a valid way of measuring a reaction rate. Here, all of the above will work because color can be turned into a number. Computers do this all the time. That's the only one that's kind of iffy, is the color of a reactant or product. You actually can measure how blue or how green something is. All right, so there you go. So yeah, so anything that can be given a number is a valid way to measure the rate of a reaction. Okay. All right, considering the reaction equations below, this is a reaction mechanism. That's what we call these. These are reaction. So this is a reaction mechanism. And if you guys remember, this is how reactions actually occur. They don't occur in one step like we talked about in previous chemistry classes. They actually occur usually over multiple steps. Again, partly because the way reactions work is things collide, and if depending on the reaction, having a bunch of things colliding all at once doesn't always work. So reaction mechanisms usually describe how 2 or 3 things collide over several steps until you get the final product. Anyways, with this reaction mechanism, you can usually boil this down to an overall reaction. So in this case, the overall reaction for this is going to be as follows. I'm going to cut out everything that appears on both sides. Okay, so the N2O2s appear on both sides, the N2Os appear on both sides, and I think that's it. So the overall reaction will look like this: 2NO plus 2H2 going towards N2, and then 2H2O like that. So this is my overall reaction. Now, even though the question doesn't tell you to find the overall reaction, it is a good idea to do that, because then you can actually answer what the question is asking for. So in this case, the question asks us for which of the following is not a reaction intermediate. Now, if you remember, a reaction intermediate are either products or reactants that show up on both sides of the reaction or both sides of the equation. So they're both products. They're products in one step and reactants in another step. But the order is very, very specific. So a reaction intermediate is a product first and then a reactant second. So basically, some step produces them early, and then another step later on down the line uses them up. So in this case, a reaction intermediate is the N2O2 and the N2O. So this one and this one, because it gets created early, then gets used up. Created early, gets used up. So these are my reaction intermediates. So this is not a reaction, or this is a reaction intermediate. This is a reaction intermediate. The question was asking us which one is not. So this one is not, because that one is just a product there. Okay. So by answering this question, even though it's not actually part of the question, it will allow you to actually answer whatever the question is asking, because there's a lot of variations of this particular question. Like I might ask, what is a catalyst? Or what is the overall reaction? Or what are the products, or whatever, right? So by writing the overall reaction equation first, you can then actually answer what the question is asking. This part's not explicitly stated to do, and I would highly suggest you do it. Okay. If nothing, to just clarify what the question is asking. Similarly, if you do end up writing the overall reaction equation, but you get the question wrong, you'll probably still get part marks, because I don't have it here, but on your previous tests, I think all the multiple choice questions are worth 2, and I'm quite generous if you show your reasoning behind why you picked it, even if you were wrong. Okay, so be mindful of that. All right, number 4. Here, activation energy. So talking about how in a reaction, every reaction, so if this is a, how did this go again? Energy was here and then time this way. In every reaction, you've got this amount of activation energy here. So this was my activation energy. And we talked about different ways you could reduce the activation energy. So there's a couple of ways you can do that. This question describes in a weird way none of the one. Well, it's just not entirely true. We did talk about them in class. The most obvious one is a catalyst, right? This is the one we talked about the most. The most obvious one was a catalyst, but as you can see in the choices given, there aren't any catalysts given there. Okay, so you have to think about what actually creates this activation energy. Okay, so catalysts lower in activation. We know this. We know this from chemistry, from biology. But what actually causes the activation energy? So this question is in a roundabout way making you think about, why does activation energy exist? And the reason is actually quite almost elementary. It's not really, well, it kind of is, because I was talking with my grade 9s and they actually mentioned that they talked about this in elementary class. And basically it comes down to, what do electrons want to do when they get near each other, and what do protons want to do when they get near each other? They want to repel, they want to push away. So it goes to reason then that if I want low activation energy, I want lower amounts of repulsion, Okay, so how can I achieve low amounts of repulsion? Well, this is probably not going to do it. If my reactant molecules have large amounts of electrons and large amounts of protons, what will the repulsion be like between those reactants? They will probably be also equally large, because electrons want to push away from electrons, protons want to push away from protons, so they kind of just want to push away from each other. So this is probably not these ones. Okay, probably not those ones. Okay, what about this? Proper collision alignment. Well, if you remember from Chem 11 and basically like all chemistry, molecules come in different shapes and sizes, and depending on the arrangement of those molecules, then maybe the collision alignment will actually affect how much repulsion occurs. I'll give you an example with like water. So here's water. If you remember from Chem 11, water is very polar. So the oxygen end of, so here's hydrogen, oxygen. The oxygen end is very, wait, no, not positive, very negative. The oxygen end is negative because it's more electronegative. So the oxygen end is negative while the hydrogen end is positive. So if I'm trying to combine water molecules and I'm trying to ram the water molecules like this is probably going to increase my activation energy, because I'm trying to ram two negative ends together. So that's probably going to increase the activation energy. If instead I rearrange the water molecules so they look like this, have my hydrogen there, have my oxygen there, have my hydrogen here, there we go. If I try to ram these ends together, well, that's probably more likely, because I've got a negative and a positive, and they will probably try to attract each other much easier than if I were to ram the two oxygen ends together. Okay, so this is going to be the answer for this, because again, activation energy kind of arises from just how electrostatic forces work. Okay, this is the obvious answer, but the obvious answer is not listed there, so it's going to make you guys think a little bit more. Alright, so remember that. Activation energy at its heart is caused by these lower amounts of repulsion, or sorry, not lower amounts of repulsion. Activation energy is caused by repulsion, partly caused by repulsion. And you can reduce the amount of activation energy by giving favorable arrangements. Okay, and actually, in all honesty, that's what a catalyst does. If you guys remember from biology 12, catalysts like to arrange things so that they can join together nicely. And all the catalyst really does is it arranges the molecules so that they have proper collision alignment, so things can react. That's why they call them lock and keys. Lock and keys. All right. Next question. Okay, so consider the following reaction. We have carbon dioxide, water producing, this is a reverse combustion, reverse combustion reaction. Okay, which of the following best describes entropy and enthalpy change of the reverse reaction? So this one you have to remember what reverse and forward reactions are. So reverse reaction goes this way, forward reaction goes that way. Okay, so even though this is a reverse combustion reaction, the way it's written defines what your reverse and forward reactions are going to be. Okay, now entropy, gotta define these. Entropy, I think, was introduced this year. Yes, entropy, and this is randomness. Okay, you guys will have to let me know if any of you guys attempted the entropy excuse for not cleaning your room. I'm waiting for that. Penny hasn't learned about entropy yet, but I think she would totally use it on us, and I don't know how we'd react to that. Anyways, so entropy is randomness, enthalpy is energy, heat energy. Technically it's thermal energy, and if you remember from, was it Chem 11 or physics? I forget. I think Chem 11. No, physics. I talked about it in physics. Physics 11, thermal energy is total amount of energy in a system. So chemical systems generally want to go towards full randomness. Okay, so chemical equilibriums, I'll write that, not equilibriums, reactions, sorry, reactions. So chem reactions go to more random and less energy in general, less energy. Yeah, that's what they want to do. So a chemical reaction wants to go to a state of extreme randomness and a state of low energy. Okay, now randomness is generally determined by state of matter. And energy, this is determined, you can tell an energy change based on exothermic or endothermic. Okay, so in this case, which of the following best describes the entropy and enthalpy change of the reverse reaction? So the reverse reaction is going from solids and gases to gases and liquids. Okay, so it's going from a highly ordered state, which is the solid, and a random state of gas, to a random state of gas and then liquids. So basically, because we have a gaseous state here and a gaseous state there, the amount of randomness provided by the gases is kind of nullified. Even more so because we have 6 gas molecules on the product side and we have 6 gas molecules on the reactant side. So the amount of randomness due to the gas particles, gas molecules, is effectively the same. So that doesn't matter. What matters then is the other materials. So here, the C6H12O6 is 1 solid going to 6 liquid. So that is much more random. So the reverse reaction, the entropy will increase. Okay, because you're going from a more ordered solid state to a less ordered liquid state. The gases are still the same, doesn't matter. Okay, now the enthalpy change, I'll erase some things here. The enthalpy change depends entirely on where this shows up. Okay, so if you remember, an exothermic reaction, the energy appears as a product. Energy is a product. And an endothermic reaction, the energy is a reactant. Now, this question, we are interested in the reverse reaction, so we're going this way. The reverse reaction, the energy is a product of the reverse reaction. So this means that enthalpy will decrease because an exothermic reaction is a decrease in energy. So in this one, enthalpy will decrease. Okay, so we have an increase in enthalpy, increase in entropy, and a decrease in enthalpy, so this will be my answer here. Okay. So remember that. Entropy is randomness, and that's all entirely based on state of matter. So gases are the most random, solids are the most ordered, and an energy depends on where the energy appears. If energy is a product, it is exothermic, so that means exothermic reactions have decreasing enthalpy. Endothermic, that's energy is a reactant. Endothermic reactions have increasing enthalpy. So maybe I'll write that down here. So entropy, or we'll write both down, I guess. Entropy, solid, liquid, gas. Entropy increases this way, and then enthalpy, exothermic, endothermic, so enthalpy increases going that way. Okay, so for entropy, solid, liquid, gas, as you go towards a gas, the amount of entropy increases. With enthalpy, going from exothermic or endothermic has increasing enthalpy, exothermic has a decreasing enthalpy. Okay, all right. Okay. Chemical equilibrium, so this was basically boils down to Le Chatelier's principle. If a chemical system is in equilibrium, more product is added. Which statement best describes what will occur? So Le Chatelier's principle basically says if your chemical equilibrium is changed, then the reaction, provided the container is closed or the system is closed, will basically undo the change. And what that means is that the forward and reverse reactions will adjust until a new equilibrium is reached. So in this one, if I have a simple equilibrium like this, more product is added. So if I increase the amount of product, my chemical system is going to want to reduce the amount of product. So my chemical system will go this way. Okay, which means that the reverse reaction will occur more often than the forward reaction to use up all of whatever I've added in there. So that'll be this one. So reverse reaction will occur faster until another equilibrium is reached. Okay. The forward reaction still occurs, right? The forward reaction still occurs. So statement C is not entirely incorrect, but we're asking for the best. The best answer is this. The reverse reaction will occur faster than the forward reaction until you get to a new equilibrium. Okay. Okay, question 7 is basically the same, only this time I give you an actual equilibrium. So this one I am increasing the amount of CO2. So which way will my equilibrium go? My equilibrium is going to move this way because I want to, the reaction will want to use up the CO2. And when I use up the CO2 by going this way, what will happen? Well, all my answers revolve around what happens to this substance. If my equilibrium is shifting backwards, then the amount of this substance has to go up. So equilibrium will shift towards the reactants, and then, yeah, so it'll be this one. Okay. This question has many variations because it'll basically be, okay, which way will the equilibrium shift? And then I could ask about different substances in the equilibrium. So it could be maybe ask what will happen to this one, or what will happen to the amount of energy, or whatever. Okay, but as long as you understand how the equilibrium will shift, then it's easy to tell which substances will increase in amount and which substances will decrease in amount. Okay, so be mindful of that. Okay, actually, in all honesty, you could just draw this shift, and everything kind of falls out from that. All right, this next question's kind of tricky, and I've had students answer this in one of two ways, and both ways I actually accepted. The first and simplest one is simply this, because we know that solids do not affect equilibrium. Okay, because of the way that solids behave in real life, they don't actually affect equilibrium. But other students have also answered this with a note: if only one liquid is present. Okay, and I've marked that correct as well. because it is correct with that note. Liquids by themselves can affect equilibrium, so it's kind of ambiguous. So if you just answered with liquid, it's very ambiguous, and we'll probably just mark it wrong. The other two, because concentrations can change, the other two are incorrect. Okay. All right. Okay, this one is, so now I'm getting solubility. So which best describes equilibrium of saturated solution? Remember, saturated solutions, you have a solid which is dissolving into some kind of aqueous mess. Yes, aqueous. And so that's what happens to a solid, but at the same time, at equilibrium, the exact reverse also happens. So the reverse will happen, so forward reaction, but then the reverse will happen when it's saturated, is that some of the dissolved ions will go back and reform the solid. There we go, that's better. So what happens here is that the rate of crystallization, so that's the ions reforming the solid, is equivalent to the rate of dissolving, which is the solid turning into ions. So that's what happens in a saturated solution. Okay, easy to see. If you ever want to do this at home, just add salt or sugar to water until it stops dissolving. Once it stops dissolving, then you saturated it, and then you'll have some solid amount of salt or sugar, and then you'll have a bunch of ions or dissolved amounts after that. All right. Here's energy reaction diagram, so kind of jumping back into reaction kinetics. Lots of things you could ask. I would highly suggest that if you see a reaction energy diagram like this, that you simply start off by labeling what the relevant energies are before you even attempt to start it. Like that. Yeah, I think these are three most relevant ones. Yeah, so forward activation energy, reverse activation energy, and then delta H. So before you actually look at the question, I would highly suggest you do this. And there's a couple of things I remember noting about this, is that make sure you put the right energies in the right places. Okay, so be sure to review that. Be sure to review that. Having said that, you will probably see a question like this, and if you don't review what all those energies are, then I don't know what to say. I don't know what to say, especially after we just told you guys to just review those. Anyways, all right, so now that you've labeled all of the energies, now answering the question becomes really easy, because okay, so what's the activation energy of the reverse reaction? Well, that's this one here, and that's like, okay, well, now I just go from 100 to 500, that's 400, there we go. Okay, I could easily ask, what's delta H? Delta H is this number, so that'd be 200. What's forward activation energy? That's 200, it's 300 to 500. So yeah, so labeling your energies, really important. Make sure you know what the energies are. Okay. Now to throw sort of like you could totally throw something into the mix, something else into the mix here. Like what if there's a catalyst and you had something like this, right? Then you'll have to, like, hopefully there's enough room on your paper, but then you'll have to figure out, okay, well, now that I have a catalyst, what changes? That changes and that changes. So now you've got a different forward activation energy and a different reverse activation energy. What doesn't change? This doesn't change. That still stays the same. Okay. So watch out for that. And yeah, make sure you understand how to calculate forward, reverse, and delta H energies. Okay, because it becomes very, very important. All right, number 11, back to solubility stuff. You will find that in my efforts of giving everybody a unique test, that I will probably have the order of questions in a very, very bizarre way. So don't expect everything to start off with reaction kinetics, moving into equilibrium and then solubility equilibrium. For all you know, you might get the test that starts off with solubility equilibrium and works backwards. Okay, so make sure you know what you're doing. All right, so this question says if the trial ion product is equal to the KSP of a salt. So this was when we were talking about trial ion product, and then we had 3 cases. Technically only 2 cases. One was Q greater than KSP, one was Q equal to KSP, and then one was Q less than KSP. These 2 both result in precipitate formation, and this one, no precipitate. I think George did a very good job of basically guessing what that lesson was, because I think that was the day where we were discussing something and it took all block to try and explain it and nobody understood it, so I made a video after the fact, which I think explained a little better. So hopefully you guys understand that bit. But yeah, the lesson of that day was basically watch the video about this, and yeah, George made a good inference and he was correct. Anyways, so if Q is equal, so that falls into this category, precipitate forms. There we go. There you go. That's all that matters. The salt has nothing to do with KSP, so these answers have no meaning. They're just kind of there to throw you off a little bit. Okay. This question number 12. I had a similar question on your solubility exam. Different compounds, a very, very similar question. So we're asking for what is least soluble. So basically this is, you're looking for a low soluble compound, low soluble, and lowest KSP. Lowest KSP. And I think I tricked a few of you because, well, depending on the variant of the test that you had, a few of you were looking at strictly KSP values and you completely neglected the alkali metals that were present. I think the variation on some of the tests before spring break were which compound had the highest solubility, and there were a bunch of low solubility compounds, and immediately some students went to go look for the KSP value that was the smallest, so they just used that. And I think I had one alkali metal compound which doesn't have a KSP because it's an alkali metal, because they always fully dissolve for the most part, so they couldn't find that, so they just ignored it without bothering to check the solubility table to see if it was a fully soluble compound. Anyways, so yeah, so watch out for that. So you're gonna, depending on what the question, how the question is phrased, you're gonna look for either low soluble and lowest KSP, okay, or use the solubility table. Use solubility table. Okay. In this case, this particular question, I think, requires use of the solubility table, because if you look carefully, the only one that has a KSP value is this. This has a KSP value of something. It's silver chloride. It has a non-zero KSP value. Wait, I shouldn't say that because they all have non-zero KSP values. What am I talking about? Erase. Yeah. So the silver chloride is the only one with a KSP value in our tables. The lithium nitrate, cesium sulfate, and strontium hydroxide, you won't find those on the KSP chart, but you'll find them here in the solubility table. And the solubility table will show that these are all, soluble. Those are all soluble. Okay, that actually kind of gives you a clue as to which one has the least solubility, because if only one of them has a KSP, then this is probably the one that is has the least solubility. Okay. With that said, I'll probably try and find a low soluble combination of anions and cations that is not in your KSP table, and that will probably throw a bunch of you guys off. Unless you've watched this video, in which case you know exactly what to look for. But again, you guys will all have different versions of the test anyways. So yeah, know how to use these 2 tables. Okay, understand that. All right. Oh, hey, I'm done all the multiple choice review stuff. All right, 13. So here is another question, very similar to this one, number 3. What you want to do for this, just like before, is write the overall reaction equation, which I actually kind of wrote down here. Okay, so that's so do that first, actually. Interestingly enough, in the process of writing the overall reaction equation, you can actually figure out all the other stuff. So canceling out things that appear on both sides. Remember, if it's a product first and a reactant, that is a reaction intermediate. Okay, the OH appears on both sides. Product first, then a reactant later. HIO shows up on both sides. Product first, then reactant later. H2O shows up on both sides. But this is reversed. So notice H2O shows up. Let's write that in a different color. There we go. So here H2O shows up, but notice it starts off as a reactant and ends up as a product. Those are catalysts. Again, we mentioned in previous classes, either chemistry or biology, that catalysts don't actually take part in the reaction or don't get used up in the reaction, but they actually do. They just get remade later. Okay, so if it's a reactant first, so catalysts are reactant first and then product later, product second. Okay, and I think that's it. So there you go. So then overall reaction equation will be whatever is left over on the reactant side, turning into whatever is left over on the product side. There we go. All right. Now the next part is what happens to the equilibrium. So if I add more ClO minus, so let's change this. So if this goes up, which way will the reaction go? Well, based on Le Chatelier's principle, if I increase this, the system will want to decrease it, so the system will want to go forward. Okay, and here you can say basically system goes forward. You can say forward, you can say shift to products, Either way is fine. You could draw an arrow just like I've done here, and then just say C arrow. That would work too. But yeah, do make it explicit. Okay. Alright, E. Identify 2 ways you can increase the rate of the forward reaction, aside from adding another catalyst. Okay. That one's easy because you've already mentioned this one answers it already. That's one way to do it. Okay, that's one way to do it. Add more ClO. 2 other ways. Add more I minus. Okay. You could also remove Cl minus or remove IO minus. We can't say add or take away heat because we don't know if this system is exothermic or endothermic. With that said, maybe I'll add that in as a question. I'll explicitly state whether this reaction was endothermic or exothermic, and then that would be another way to increase or decrease the forward reaction. Okay. Yeah, speaking of which, with regards to endothermic and exothermic reactions, do review how adding energy affects the equilibrium for endothermic and exothermic reactions. F. So it's same question. That's not really, this one's just right. If the overall reaction rate was this per minute, how long will it take to produce 1 kilogram of product? This is a very almost, no, it's not quite elementary, but if you have the following 2.5 grams for every 1 minute, and we want to multiply this by some number of minutes to get 1 kilogram, which is, let's convert that to 1,000 grams and call that X. Yeah, just simple algebra from here. So the number of minutes will end up being 1,000 grams divided by 2.5 grams per minute. So that'll be some number. I want to say 400 minutes. No, it can't be that. Oh, maybe it is. Maybe it's 400. Okay, quick math on top of my head. If I'm wrong, let me know. I think it's 400. 4,000. No, it's 400. I'm pretty sure it's 400. Somebody will correct me. Correct me in chat. Correct me in chat. All right. Okay. Here now on to equilibrium. KEQ. So I think this question will require the use of an ice table. Not every question that's in this topic requires an ice table. It might not. Okay, but basically, let's read the question. So here's a reaction. We have KEQ. It tells us we add some amount of this, some amount of that. And then at equilibrium, oh, this is important. At equilibrium, it tells us how much we have of each of these. Okay. Now, trying to remember if I did all of my ice tables in terms of moles or in terms of concentration. Regardless of how you do it, as long as you are consistent with using moles or concentration, it should work out just fine. There are some, actually, I don't think there's actually any advantage in using moles because it requires some calculations everywhere. All right, anyway, so let's set up my ice tables. I think I'm gonna need one. Ice. Your textbook has it as an initial change equilibrium. They use the delta symbol. All right, so CH4, we have some unknown amount. We're going to assume we start with 0. This will change by some amount. This will change by some amount. Now again, the reason for the 2 is because I've got 2 of them. This will change by some amount. It's not x, y plus y, and this will be plus 4y. And the reason for the 4 is because of that. Okay. At equilibrium, we now have the following. We know that we have 0.2 of that. Have 0.3 of this. Y and 4y. Okay, so here is what we know. Notice that I don't have any variables for these amounts, and that's partly because it tells me at equilibrium I have these amounts. Okay, so it doesn't matter that I have unknown amounts at the beginning and that I know they change by some amount. That doesn't matter because I know how much I have at equilibrium. That's all that matters. Okay. All right. So it tells me I have moles, so I should actually write that in as moles. Okay, this becomes semi-important because, oh, maybe not, because I have a container. Okay, I have 1 liter container. The reason it sort of becomes important is because in order to calculate the moles of CS2 and H2, I have to use KEQ. And if you recall, KEQ deals with concentrations. So KEQ is concentration of products, so concentration of CS2 times concentration of H2. But again, I've got 4 of them, so I've got to do that to the power of 4. Concentration of H2 to the power of 4 over concentration of the reactants, which is CH4, and this is H2S, but I've got 2 of those. Okay, so that's my KEQ. Now, because I have this in moles, I have to convert these mole amounts into concentrations, which is easy enough because I have a 1 liter container. So just divide this by 1 liter. Divide that by 1 liter. So that'll give me my concentrations here. So this is going to be surprisingly easy. Yeah, 0.2 molar, 0.3 molar. Okay. And then I should have written smaller and given myself more room. Oh well, it's okay. And then we've got the unknown amounts here and the unknown amounts here. Again, because we have unknown amounts, this will just be, it actually doesn't matter that, yeah, these unknown amounts can just stay unknown. You don't have to worry about the division here because we honestly don't know what the mole amounts are, so we don't actually know what the concentration is, so we can just leave them as unknown. No need to convert or do any kind of fancy division. So even if it wasn't a 1 liter container, mathematically these amounts can stay unknown and you don't have to worry about them in the conversion or in the calculation. Anyway, so putting these numbers into calculation, we'll get the following. So here's the concentration of CH4, concentration of H2S. So going back to my KEQ equation, I think I'll have room here. Actually, maybe I'll just zoom in a bit more. Alright, so KEQ will then be concentration of CS2, which is unknown, and then concentration of H2 the power of 4 over top of concentration of CH4 concentration of H2S squared. Putting in some numbers, CS2 is going to be Y, concentration of H2 is going to be 4Y to the power of 4, and then concentration of CH4 is 0.2 and concentration of H2S is 0.3, but that'll be squared. And then carrying this calculation out, simplifying this, I think 4 to the power of 4 is 256. Y times y to the 4 is y to the 5th, and then this will be 0.2 and this will be 0.09. And then this is all equal to 100. Why 100? Because I think the question tells me that. Yeah, KEQ is equal to 100. Yeah, then after this, it's just a bunch of algebra to solve for y. And then once you solve for y, that'll be the concentration of, that'll be the concentration of CS2. Then 4y will be the concentration of H2, and then it's just a simple molarity calculation to figure out the number of moles, which is what the question is asking, number of moles. There you go. Okay. So that's how we handle something like this. There were, how many different, I think there were like 4, no, I think there were 6. 4 or 6 types of equilibrium problems, so I highly suggest you all review the different types of equilibrium problems because you will probably get one of them, maybe 2. Alright. Okay, 15. Back to solubility. Is that the last one? No, it's more. Okay, so 15 is back to solubility. So what mass of silver iodide will dissolve in 250 milliliters of water? Assume saturated. That's important because now we can write the following. In a saturated solution of silver iodide, we get the following equilibrium taking place. We get some amount of silver ions, some amount of iodine ions, and there we go. And this equilibrium will be governed by the KSP of silver iodide, which I did not remember. I did not memorize it, but it is in your data booklet, I believe. Yes. So that's kind of the first thing you want to figure out. And remember that KSP, the KSP of silver iodide, arises from the equilibrium or from this equilibrium, which is the concentration of Ag plus times the concentration of I minus, all divided by the concentration of the solid. But because it's solid, we don't really write it in. So this is what it looks like. Okay. Now, since we don't actually know how much silver iodide has dissolved, we can write the following. We can write, okay, if I have some amount of silver iodide, that will dissolve into some amount of silver ions and some amount of iodide ions. So my equation here will just become KSP equals x times x. So this will be x squared. So whatever the KSP of silver iodide is, that'll equal x squared. So we can use this to do the following. We can use this to calculate the concentration of silver ions. Or if you feel like it, you can use this to calculate the concentration of iodine ions. It doesn't really matter at the end of the day. In this particular case, it might matter if we're using something like not silver iodide, like maybe strontium iodide or silver carbonate. Basically, if this 1:1:1 ratio isn't 1:1:1, then this equation will have to be adjusted. So make sure you understand how to set this up, because you may not receive an equilibrium that is 1:1:1. Okay. Anyways, so once you figure out what the concentration of silver or iodine is, then you can use that, because we have this 1:1:1 ratio. Then in this particular case, this will also equal the concentration of AgI. And the concentration of AgI is really just moles of AgI divided by volume. And since we have the volume, our volume is 250 milliliters, we can then use the concentration of AgI to find the moles, given we have 250 milliliters. And once you have the moles, then you can go from moles, you can convert that into mass. That's what the question is asking. What mass? I realize this conversion here is kind of Chem 11-ish, but it's still important to know how to do that. If you need to review your Chem 11 notes, hopefully you didn't burn them and you still have them with you. Okay, there you go. So that's the entire process. All that's left to do now, I suppose, is actually put in the numbers, and that requires you to basically find what is the KSP of silver iodide, which should be in your data booklet. All right, I think this is the last question. Yay, last question. All right, so here, a solution containing the following ions: magnesium, calcium, strontium. We're slowly adding potassium carbonate to the solution. So I'm gonna write the formula for potassium carbonate here. Good idea to do that. What are the possible precipitates that form? Potassium carbonate will turn into potassium ions and carbonate ions. Now the positive ions won't ever react with other positive ions, so we don't have to worry about that. So all we have to do is check, okay, which of these following combinations, magnesium carbonate, calcium carbonate, and strontium carbonate, are actually low soluble compounds? Well, it turns out that they all are, because carbonate is low solubility with everything as far as we care about, except for hydrogen, alkali metals, and ammonia. Ammonium, not ammonia. So that's easy. Okay, that's easy. Keep in mind though that if it's not carbonate, like let's say this was a hydroxide, check solubility table. So once you've written down the combinations of possible precipitates, check the solubility table to confirm what you wrote down, to confirm which are low soluble. Okay, so if this was a hydroxide, like potassium hydroxide, you get magnesium hydroxide, calcium hydroxide, and strontium hydroxide. But when you check the solubility table, you'll see that the strontium hydroxide is actually not soluble. Okay, so in this case, this was relatively easy because, well, everything is low soluble with carbonate. Now B, which precipitate would form first, and I realized this actually gets a lot of students. Show your calculations. Okay, this is actually kind of misleading. Although admittedly, there was at least one person who on the either on the test or the quiz who actually showed calculations that made sense to show that which one performed first. But really all you have to do is compare KSPs. Compare KSP. Okay, then whichever is smallest. Whichever is smallest. And that's all you really have to do. Whichever is smallest forms first. Now, if you were to actually do this with actual calculations, you would take your KSP calculations. So like, let's say magnesium carbonate. So if you were to do this, you would actually do this and then figure out, okay, we know the concentration of carbonate because we have this. The concentration of carbonate is 0.001 based on this dissolving equilibrium here. Okay, and then the magnesium would be X, and then whatever your KSP value will be here. So then X will be whatever KSP is divided by 0.001. And then you could compare the X values of the varying salts. Or not salts, ions, the X values of the various metal ions. And whichever one is smallest will form first. For a similar reason that it requires the least amount. Okay, then compare X values. Smallest X will precipitate first because that's the least amount. Okay, there we go. That's actually very ingenious because I think this is the first time anyone's ever attempted to explain this question using this calculation properly, at least using that equation properly. All right, C, describe one way you can increase the solubility of precipitates. Now, some of you will mention add heat, and while this is a viable option for a good many low soluble compounds, not always. Okay, this only works if the dissolving equation is endothermic, if dissolving is endothermic, which again, like I said, it's usually the case, but there are some cases where it's not. So this is not a good answer, not the best answer, I guess. The better answer would be to precipitate the carbonate or precipitate the metal ions. Because as you precipitate out the carbonate ions, you effectively force, let's say we have like this, and then you get 2 plus CO3 2 minus. If you cause this to decrease, then the reaction has to increase forward, which will then cause this to decrease. Okay, so there's really only one way to increase the solubility of the precipitates, and that's quite simply just either precipitate this, or you can precipitate the metal ions out. Okay, admittedly this creates like more low soluble compounds, but the question doesn't seem to care overly about that. Just how could you increase the solubility of this? Okay. All right, there you go. So that's basically what we did for this first semester, is reaction kinetics, equilibrium, and then solubility equilibrium. Now when we get back from break, we'll talk about acid-base equilibrium, okay, for that first week. Anyways, all right, so thanks for sticking around, and if you guys need to review this some more, this will stay on my, it'll stay up. There's no reason for me to delete it. Although future generations, they might wonder who the heck I'm talking to or what I'm talking about, because I did reference a few of you guys, so that's okay. They can sit around mysteriously wondering who the heck are these people. Anyways, you're very welcome, and again, enjoy the rest of your break. If you guys have any questions, you guys know how to get a hold of me. All right, have a good rest of the last week of spring break, everybody.